Okay, good afternoon, ladies and gentlemen. It's a great pleasure to be here again. Everything is nice and fine, and I'm in particularly pleased to see your success to get this program, and I wish you good luck with it. So I was asked to give a short presentation on electron interaction with biomolecules, a subject which we were involved over the last 10 years or so. And of course, it's a pleasure for me to give this short presentation. So, before starting with biomolecules, for those people who are not very familiar with electron-molecule interactions, just a few comments. If you consider the interaction of electrons with molecules, this is a polyatomic molecule. You can have a process which is called direct scattering. So the electron at some energy simply collides with the molecule. You can get excitation. This is usually electronic excitation. And of course, if the energy is sufficient, you can get ionization. If you go down at too low energies, you may have also rotational or vibrational excitation, but the cross-section for this kind of excitation is low simply from mechanical reasons. The mass of the electron is much lighter than of a molecule, so if it hits the molecule, vibrational excitation is not very likely. So there is a more interesting process. If you go down in energy, maybe to 5 electron volts or even below 5 electron volts, at particular energies and angular momentums or impact parameters, you may have a process which is called resonance scattering. So a particular interaction between the negative charge and the molecule provides conditions that, classically speaking, the electron is orbiting around the molecule and is eventually kicked off. Then you have resonance scattering. A closer view on this process in the case of a diatomic molecule. So the electron hits the molecule, orbits around the molecule. In the language of chemists, the electron stays in an unoccupied molecular orbital for some time. If this is an antibonding or even if it's a bonding orbital, the molecule may start to vibrate and the electron may be kicked off. But during the lifetime of this orbiting state, of this compound state, you may have also, if you have particular energetic conditions, you may have also dissociations. This means the electron stays on one part of the molecule and the molecule breaks. So this is a quite effective process to break chemical bonds at energies which are considerably below the energy of a bond dissociation energy. So the last process is called dissociative electron attachment, and this is a process which we will consider in some more detail. So one way to look on such processes is in a schematic view, is a so-called beam experiment. So you have an instrument which produces a beam of electrons, which is quite easy, just emitting from a filament and making particular things, that you have a well-defined beam of reasonably good energy resolution. And then you have a molecular beam. This can be single molecules or clusters. In the case of biomolecules, you usually need an oven in order to evaporate these molecules, get them in the gas phase. And then you have a collision between the beam of electrons and the molecular beam. You may form this compound state. And this compound state may live long enough that you can detect it by mass spectrometry, or the molecule breaks apart and you can detect a fragment ion, X minus. And the usual way is to just scan the electron energy and look at which energies does a particular fragment appear. So before going to biomolecules, one example of the prehistoric times, deep into the last millennium. So when the ozone problem was a problem, so these were the propellants, one of the molecules here, which was considered to destroy the ozone layer. Because this molecule is photolytically very stable, strong bond dissociation energy, so if you shine light onto this molecule, it's very stable. You need to go far into the ultraviolet to break this molecule apart by photons. But as you can see here, if you use electrons, it's quite different. So what you see here is just the energy scale. Here is 0. And this is just the intensity of the ion. So what you see Cl minus. So you form at an energy close to 0. The electron comes with essentially no energy, orbits around this molecule, and it breaks apart into Cl minus and the complement, namely the radical. And it does this with a quite high cross-section. So the cross-section is orders of magnitude larger than the geometrical cross-section of the molecule. So to destroy the molecule with high efficiency just without any additional energy, and you selectively break a bond if you shine electrons with energies close to 0 onto the molecule. This has simple energetic reasons, because you cannot break another bond, and the driving force for this reaction is just the high electron affinity which you gain in the process, which is in this case a bit higher than the binding energy, the Cl binding energy. So if you go higher in energy, you can see other fragments, F minus, and the complement here, CCl minus. So in this case, if you shine in with about 3.5 eV, you selectively break the CF bond. And the electron sits on the F minus or on the CCl3 minus. So it's not completely selective. If you enlarge the scale here, you see a little bit of Cl minus also. So in a very, very simple language, you would say, in reality it's much more complicated, you would say here, you occupy with the extra electron an antibonding CCl orbital, and in this case an antibonding CF orbital. In any case, this is the case what happens if you shine electrons on molecules like that. halogen-containing molecules. You all know that halogens like electrons, and no wonder that dramatic things appear. Now, in biomolecules, things may look different. Yeah, just to mention, this has applications, this kind of selective bond breaking, also in surface tunneling microscopy. So you don't have really free electrons, but tunneling electrons, and these electrons may also induce particular selective bond breaking, which you can study on a molecular level, which was shown by these people here, particular excitation or particular bond breaking. So what about biomolecules? This is a typical biomolecule, thymine. There are no fluorine or chlorine around, just nitrogen, oxygen, carbon, and hydrogen. What will happen if you shine an electron beam on this gas phase molecule, the DNA base, the single DNA base thymine? So we did this kind of experiments about 10 years ago when we started that business. And this is an example of all 4 DNA bases, thymine, adenine, cytosine, and guanine. And you can see that at quite low energies, below the level of electronic excitation, there is a dissociative electron attachment process and a particular process, namely a process which is the following. An electron comes, forms this transitory compound state, and then the compound state breaks apart, kicking an hydrogen, neutral hydrogen atom off, and the electron stays with the molecule, forming a closed shell negative ion. And this process operates, as you can see, at quite low energies, significantly lower than the CH bond dissociation energy, and the driving force, the energetic driving force of this reaction is the high electron affinity of this radical, which you gain in the process. So you have a reaction in these molecules, hydrogen loss, and you can ask the question, from which side of these molecules you will lose the hydrogen. It can be one of these positions here, and we did some isotope labeling experiments, and these experiments showed that only these 2 positions, the nitrogen positions, are involved. There are no particular energetic reasons. The bond dissociation's energies are not so different, but only these positions are involved in the hydrogen loss. So this is related to something which was addressed this morning: radiation damage, eventually radiotherapy. So we know high energy radiation is damaging DNA, but the really molecular mechanism behind it is not very well understood so far. What we know is, well, this is a statement which is accepted. The damage is due to a variety of reactive intermediates and so on, and abundant intermediates are ballistic electrons. So a ballistic electron is an electron with some kinetic energy above the conduction level, or whatever you will call this, of this condensed material. And of course you produce also OH radicals. as we learned this morning by Kevin Price. So we have a situation which is schematically shown here. You have a high energy quantum which produces secondary electrons at an initial energy up to a few tenths of eV. This electron collides with further components, makes further ionization events, excitation events. The electron is then slowed down, and before being solvated, it may attach to a particular site of the DNA and do something. So this is an energy scale, this is a distance scale, and this is a time scale. So we look for events which occur in a very early stage after the impact of a high energy quantum, not on a biological scale and not on a chemical scale, just the scale picoseconds and below, but a scale which is eventually decisive for the overall story. Okay, so this is a well-known picture here. Quite some years ago, Leon Sanche and co-workers showed, in fact, on plasmid DNA, that you can induce double-strand breaks and single-strand breaks by shining electrons to DNA. And this efficiency of strand breaks has some kind of resonance structure. So the suggestion was already that some resonance process may initiate these single-strand breaks or double-strand breaks. So they extend the electron scale to lower energies. You can hardly see it. But in a paper a bit later, they showed that close to zero energy within a resonance structure, you can also produce strand breaks in DNA, but only single-strand breaks in that case. So the question is, what is the molecular mechanism between which leads finally to these strand breaks? I showed you already that the DNA bases are active. They capture electrons at low energies in the range between 1.5 and 3.5 eV. And has that to do with strand breaks? If a thymine captures an electrons, you need to break a bond here and here. And there was a theoretical model which was published some years ago, the electron transfer model, saying that in this case, cytosine acts as an antenna for these low energy ballistic electrons. It captures electrons. These electrons are transferred to the backbone and induce a strand break here. So in a theoretical model, it was predicted that you may induce strand breaks by initially capturing an electron by the DNA base. Well, the question is then, what about the other components? What about the sugar and the phosphate groups? So this is a part of a single strand here. What do the sugars do and the phosphate group do? Are these compounds or these components also sensitive to low energy electrons? And we investigated some sugar molecules quite detailed, and I cannot go into details here, but what you can see here, these are just mass units here. We did some isotope labeling experiments, and you could see that sugars are sensitive to electrons already close to 0 eV, so you don't need energy to break the sugar apart. In this case, the sugar breaks apart by just losing one or more neutral H2O units. And isotope labeling experiments show you that always this C5 position is involved, which would mean for a sugar molecule coupled to DNA that you may eventually induce a strand break. The story is a bit more complicated because what I showed you was ribose. Sugar in DNA is deoxyribose, so we use this as a model compound to study this molecule in the gas phase, and this molecule is also sensitive towards electrons at very low energy. The molecule breaks apart. Okay. Finally, electron attachment to the phosphate group. This is phosphate group coupled to the neighboring bases. We investigated this as a model compound for the phosphate group in DNA. And what you observe is also things going on at quite low energy. This is, for instance, the molecule which is subjected to the loss of this entire group here, which would mean a strand break. So what do we know about the story of the molecular mechanism? We know that the nucleobases, as I showed you, act as antennas, and that the electron, according to this model, may be transferred to the backbone, but also the sugar molecule is sensitive, or the sugar unit is sensitive to low energy electrons, and also the phosphate group is sensitive. So the conclusion is different mechanisms may eventually contribute. So what can one do? One can try to transfer larger units into the gas phase, which is not so easy. Thermal desorption, you may not succeed in transfer larger units intact into the gas phase. You need to use. But this colleague in Poland recently succeeded to transfer an entire nucleotide, which means a DNA base, a sugar unit, and a phosphate unit. DCMP, this is for deoxycytidine monophosphate. So she apparently transferred this as an intact molecule, which was carefully checked, as I could see, into the gas phase. And the analysis of this experiment, which is based on the particular fragments which are formed, but also on the energy profile of the fragments, because the energy profile carries the initial attachment process. And the analysis of all these reactions led to the conclusion that at least in this deoxycytidine monophosphate, bonds which are involved in a single strand break, which would be involved in a single strand break if this compound is coupled to DNA, you would have the majority of strand breaks by a direct attachment to the phosphate group, and also 25% by a direct attachment to the sugar, and also reactions contribute where the initial attachment process occurs on the DNA base and transfer leads finally to the strand break. Yeah, so you see also biomolecules apart from halogen-containing molecules show quite interesting effects which are apart from the biomolecular relevance, which are also from a more basic point of view quite interesting to study. And finally, I show you one example of a biomolecule, glycolamide or acetamide. You can excise the CN group here out of this molecule with electrons which at quite low energy. If you attach a 2 electron volt electron on this molecule, on that molecule, you can excise the CN unit out of the molecule, which means in the reaction which you drive, this is actually the reaction which can be followed just from thermodynamics. You have to cleave a series of bonds and to reorganize a series of bonds. So this is a quite complicated reactions. And electrons at that low energy can initiate these rather complicated unimolecular reactions. So this is my university, campus of FU Berlin. This is the new library by John Forster, this famous architect. And here is my lab. And well, this is the students of the last years. We made a bicycle expedition, a bicycle excursion to BESSY, the Berlin synchrotron radiation device recently. So I don't have the names with me. Thank you for your attention. This Innsbruck group, in particular with Stefan Denefel and many other people, yeah.
Okay, thank you, Roy, for this little talk. And yes, please.
I enjoyed this certainly. I have only one question concerning the peak at very low energy, zero. That means that the molecule, in that case, has some electron affinity. Is that right?
Has?
Electron affinity positive.
Yeah. So, well, this is a big discussion, and these processes at very low energies are also very complicated to describe. So, in particular for the DNA bases and also for the sugars, the model is that you may have, for instance, the DNA bases have a very large dipole moment, yeah? So there are models which describe the process that the electron is initially captured in the field of the dipole, yeah? And then you have some vibrational excitation, so it's a vibrational Feshbach resonance mediated by the dipole, and this couples during its lifetime to valence states. So this is the model for the sugar, and this is the model for the DNA bases. So the sugars, there are no low-lying orbitals, yeah, where the electron could enter. So the model is that you have a dipole-supported state or similar, or things similar to that. Yeah? In any case, something which is induced by the polarization interaction.
So, what's the previous results of the nucleotide that you showed?
Nucleotide, yeah?
That was just by simple heating that was brought through. That's how it's also absorbed.
It was by thermal evaporation, yeah? Yeah. But she made very careful checks, yeah, in investigating the condensed materials, that it's the entire nucleotide, yeah. But it's the limit, the absolute limit, yeah.
I have a quite provocative question.
Please. My career is over. I'm very relaxed.
It's not regarding at least the physicists in the audience, but it's mainly for our biochemist colleagues in the audience. Because one of the things that over the last years I've been discussing with colleagues here in chemistry, biochemists, and trying to convince them about the role and the relevance of these low energy electrons. Generally speaking, the answer from them is that, well, we don't care about electrons. What we actually care is about oxidation and reduction reactions. So what shall you say to biochemists regarding the role of these low energy electrons? Whether we are able or not to convince them that this is...
I know this discussion, and once people have particular models, they won't give them up, it's clear, but there are, I believe, quite some experiments, not only from gas phase. There is also a group, Q-Bin-Lu in Waterloo. They do femtosecond resolved laser excitation. They produce solvated electrons and things like that. And so there are really information now from different sides that these kind of reactions play a significant role in the gas phase. In the first step, yeah, on the time scale which I showed, yeah, the question is then, is this really, are these the really decisive steps, or are these following steps more important? Yeah, so that's my answer.
Okay, following the provocative turn of follower, you talked about clusters of the femtosecond.
Yeah.
Can you elaborate a little bit more? So are you talking about molecules in water clusters, or what is a cluster and what is the experiment that you described, but now
Well, these experiments are on single systems, yeah. Either a single DNA base or DNA base coupled to a sugar or something like that. But in the gas phase, yeah, isolated, nothing around. Of course, in the real condensed phase environment, things are much more complex. You have relaxation process. We are aware of all that, of course.
No, I understand that, but you said that the collision would be with a molecule or a cluster?
Yeah. In this case, only with molecules. Yeah. Of course, people do related experiments where they put a particular number of water to show the solvation effect and so on.
So that is possible.
Yeah.
Yeah, well, actually, I guess that because Pedro is not very used to this, but I guess that what is not clear for him is that you also have to perform experiments on clusters.
Oh yes, and in the condensed phase and so on. So we.
Beams of, let's say, model.
So this was simply an excursion into the gas phase. Yeah. So.
In the gas phase. Okay. again, thank you very much. We move.
Yeah. This is part of my efforts to attract students to the group. Okay. Great. Okay, well, first of all, I'd like to thank Paolo and the other organisers for the opportunity to join this really nice meeting and to tell you about some of our work. And I'm also grateful for the programming because Eugen's talk has really covered a lot of key issues that that I hope will be useful for the audience as well when I talk about some of the work that I want to talk about here. So I'm going to talk about electron-driven processes in biomolecules and clusters, and I'm going to include electronic excitation and focus quite a lot on that in this talk. The opening images, they're meant to represent, they're a schematic representation of an electron interacting with a cluster. In this case, this is a guanine-cytosine Watson-Crick pair. Or with a biological molecule. This happens to be pyrazine, which can act as which is interesting to study in order to draw analogies with other biomolecules, for example, nucleobases, which share some structural properties. So I'm from the Open University, and this is the main. This is what Milton Keynes really looks like. But it's the main distance learning university in the UK. And the campus is in the kind of commuter area around London. And there's a number of us at the OU who are involved in the RaBBiT program. So there's me and my group, the Molecular Clusters group. We're interested particularly in experiments probing electron collisions with biomolecules and clusters. There's the electron scattering group, which is led by Jimena Gorfinkiel. And they address quite a lot of the same problems, quite a lot of the same types of interactions, but from a theoretical and a computational perspective. There's Nigel Mason's group, and he has a diverse range of interests. One experiment that I'd like to highlight is that he carries out momentum imaging, so kind of velocity slicing technique to study dissociative electron attachment processes in a lot of detail, and he has ambitions to look at some biologically relevant molecules there. And there's also a group, a plasma physics group led by Nicholas Braithwaite, and some of their work includes looking at what happens when you expose biomolecules, including quite large biomolecules like DNA, to plasmas. Now, I'm very happy to talk to you all about those groups later on. In this talk, understandably enough, I'm going to focus on my own work, and I'm also going to talk about a little bit of where it overlaps with the work that Jimena and her colleagues carry out theoretically. So an outline of the talk. I'll first give an introduction where I talk about biomolecular excitation and ionization, which has been the main focus of our experiments so far. Why are we interested in looking at clusters? And why electron attachment, and this has been covered, I think, very thoroughly by Eugen. Then I'll talk about some of our experiments on nucleobases. I'll talk about evidence that we've seen for reactivity in neutral electronic excited states of these molecules. And I'll talk about clustering effects that we've seen. Then I'll talk about some new experiments that we're developing at the moment to try to control neutral beams of clusters for electron attachment experiments. I'll then talk about how that, talk briefly about some of the theory going on in Jimena Gorfinkiel's group, and then I'll summarize. So why are we interested in electronic excitation and ionization of DNA and RNA bases? Well, our main interest is to understand get a more detailed understanding of the valence, excitation, and relaxation pathways of these key biological building blocks. And these have attracted a lot of interest for many years from the point of view of understanding the remarkable UV stability of these molecules. And this can be relevant to understand the origins of life when we consider the harsh UV environment that existed on the early Earth. In addition, as we've already heard, electronic excitation and ionization are among the important fundamental processes which are involved in the initiation of DNA damage on the nanoscale. And so information that we can gain from our experiments, understanding that we can gain from our experiments, can be and potentially incorporated into nanoscale models of radiation damage, which in turn can guide future innovations in radiotherapy. So more generally, we're part of a community which is aiming to link data and understanding on the nanoscale in radiation physics and chemistry to effects in biological environments. And a particular tool that I'm going to talk about for the next 10 minutes or so after the introduction is contrasting fragment ion production by electron impact ionization and by multiphoton ionization. And by multiphoton ionization, so in electron impact ionization, we've got a molecule in the electronic ground state, and then we're raising it directly to an ionic state, or to a dissociative ionic state. In multiphoton ionization, in the laser fluencies that we're working at, we do so via one or more neutral electronic excited states. So if we start seeing different fragmentation patterns of molecules through these two processes, we can attribute those differences to something that's happening in those electronic excited states. So it gives us a window, this comparison, into neutral excited state dynamics. So when you look at isolated molecules, this can often lead to the most, if you like, the most direct interpretations. But the problem, as was discussed at the end of the last talk, is when you've got specific information from experiments and calculations in the gas phase, is to relate these insights to more complex systems, and particularly to biological environments. And so the perspective that underpins our work is that by looking at clusters of molecules, this can provide us with an opportunity to bridge this so-called complexity gap, because you can directly observe many of the nanoscale processes that you can also directly observe in the gas phase, but in an environment where you've got intermolecular interactions. And in addition, you can consider a cluster as a kind of nano-laboratory where you can try to modify the chemical environment specifically to change the response of a molecule to radiation. And this can be a powerful experimental tool to investigate potential ways to radiosensitize molecules. So how can clustering affect excitation and ionization? Well, first of all, when you look at molecules in the gas phase, the dominant isomeric form of the molecule is not necessarily, or the dominant isomeric forms, there may be more than one, is not necessarily going to be the same as in the condensed phase or in clusters. So that can lead to differences. You can also open channels for intra-cluster reactivity, be it radiation-induced or spontaneous. And then you can have very efficient transfer of vibrational energy from intramolecular modes to intermolecular modes. And this can provide a very efficient way to remove energy from excited molecules and can have a stabilizing effect with respect to fragmentation. And then you can also modify the energies and the vibrational coupling of excited and ionic states. So these are the types of processes that we've got in mind when we're trying to interpret our results. So I also mentioned that that's the type of work we've been carrying out so far. Our new projects are focused on electron attachment, and I think we've covered quite thoroughly the motivations for looking at electron attachment and why that's particularly interesting. Briefly, sub-ionization energy, electrons as the most abundant products of ionizing radiation. Any effects they do have in biological material, because they're so abundant, can be very significant. And the fact that they've been shown to produce double strand breaks and single strand breaks in DNA very efficiently is a major motivator to study these low energy electron induced processes in detail. And there's been a lot of this work, particularly that Eugen mentioned by L'Ensemble, inspired a great deal of work in this field. But there's still relatively little work compared to in the gas phase. There's a lot less work exploring clustering effects on electron attachment processes, and particularly dissociative electron attachment processes. So this is a very rich field to explore. And clustering can have a very important role because, as Eugen mentioned, dipole moment, long-range dipole interactions have a key role to play in electron attachment, and clustering is clustering of biomolecules. These are dominated by dipole interactions between molecules, and unsurprisingly, a dipole moment of a cluster can be radically different to of an isolated molecule, and so that can lead to significant effects on electron attachment, associative electron attachment. Modify the electron affinity. Eugen mentioned vibrationally coupled anionic states. Well, vibrational excitation is highly affected by clustering, so clearly you can expect strong effects on these types of processes as well. You can also, again, as Eugen highlighted, you can open channels for electron transfer across hydrogen bonds, which can play a very significant role in DNA damage. And you can also open channels for reactivity. For example, electron-induced proton transfer, which has been observed relatively recently in 2010 in cytosine-guanine complexes. So moving back to the experiments that we have actually done so far, looking at multiphoton ionization, electron impact ionization. So here's a schematic of our experiment. We produce our biomolecules, so our nucleobases, by heating them, simple heating, in an argon or a helium atmosphere. And then there's this argon and helium is flowing through a fine nozzle of about 50 microns diameter into a pumped chamber. So you have a large pressure difference between these two zones, and you have an expansion of gas seeded with your biomolecules in this volume. This has cooling effect. You can have coalescence of the molecules. You can have the formation of clusters, and you can gain some control over the formation of these clusters by using different carrier gases, by changing the temperature, by changing the pressure of your gas. And so we skim off this beam of either isolated molecules or a combination of isolated molecules and clusters to produce our target beam here, which we then cross either with nanosecond time scale laser pulses in the UV, or with a beam of electrons in several eV. And then any ions that we produce, we analyze in a time-of-flight mass spectrometer. This has to be a reflectron type, and that gives us some additional tools as well as giving us higher resolution. I'll talk about that a little bit later. So a quick overview of nucleobase electronic excitation. So using our laser, this is our wavelength range, 220 to 277 nanometers. This is the UV spectra. This shows the UV spectra of several different nucleobases, so the DNA bases and the RNA base uracil. And you can see that essentially, and you've got on this scale, instead of wavelength, you have it in photon energy. You can see that we're probing in our experiments using the laser. It's the lowest energy, bright electronic excited state of these molecules, which all happen to have a similar character, a so-called pi star character. And what happens after you've excited the molecules in this way? Well, they relax. Been a number of ultra-fast laser experiments where they look at multiphoton ionization with a delay between the pump pulse and the probe pulse, and in order to trace how the molecule actually relaxes. And there's a general consensus that there are two types of relaxation processes that dominate. And so you access your bright pi star state, and then the molecule stays in this electronic excited state for a very short time, for less than 50 femtoseconds. And so that, in the context of our experiments, that's too short a time for us to be able to ionize from these states. So we can't look at these states in our experiment. After however many, tens of femtoseconds, you have relaxation into an intermediate state, which also has singlet character. And that's either, for different molecules, that's either has mainly n pi star state or sigma pi star state character, and it remains in these intermediate states for a number of picoseconds. And in this case, we can ionize, in our experiment, we can probe that excited state. And then either you have, after that, relaxation back into the electronic ground state, so all that energy that you've put into electronic excitation is expressed in vibrational modes after this. And this is understood to play a key role in the UV stability of the molecules. Or you relax into a long-lived excited state of triplet character, which can stay around for nanoseconds or even longer. And this, if you like, this long-lived relaxation pathway has been observed for adenine and thymine. It hasn't been observed for uracil. And indeed, previous experiments using our kind of timescale lasers looking at uracil haven't been successful, but ours have. So this is a natural target for us to look at a bit more carefully, seeing as previous people haven't looked at it in this way. So our first thought was, okay, so are we ionizing from these triplet states, or are we ionizing from these singlet states, these picosecond timescale singlet states? And here's our first opportunity to use our clustering tool to try and find out a bit more detail. And the plan was, we knew that previous calculations had shown that hydration should strongly suppress action from our singlet bright pi star state into these long-lived triplet states of uracil. And so if we keep all of our experimental conditions the same, but we look at the uracil in the gas phase against uracil in hydrated clusters, we should see that having a strong effect on hydration if we're going via these long-lived triplet states. And that doesn't happen. We see that essentially, well, you get a change in the MPI efficiency of only about 20%. So essentially, it looks like we're not having a very big effect on the process. So it strongly points to ionization via these picosecond timescale excited states. So we know the excited state we're looking at in our multiphoton ionization. So the next thing is to try and use our tool of looking at dissociative ionization and comparing electron impact ionization with multiphoton ionization. This is the electron impact ionization mass spectrum of uracil. It's been studied by lots of different groups in the past, and people have gone a long way towards rationalizing the specific relaxation pathways that take place. And what's interesting, what's actually quite convenient for our experiments, is that all of the strong fragment ion pathways in uracil are produced for these collision experiments for electron impact ionization, begin with neutral HNCO loss. And then you have sequential fragmentation processes following that. So you get this nice convenient gap here in the mass spectrum where you can hopefully look for some new fragment ions produced due to the route via the electronic excited state. And obviously I wouldn't be talking about this if we hadn't seen one. And so this is showing a detail of the mass spectrum recorded at 220 nanometers using the laser by multiphoton ionization, and contrasting it with the detail of the electron impact ionization measurement. You can see we see this clear new fragment ion appearing with a mass of 84 atomic mass units. And we checked, there's a trick you can do, you can look at the fluence, you can look at the signal intensity as a function of your laser fluence, and you can use this to derive how many photons were absorbed in your multiphoton ionization process, and it's a 2-photon process. So this means that it rules out, we're not dissociating, we've not got dissociative ionization of the molecule and then we're ionizing one of the fragments, and that's why we've got this new peak. It really is, it's a 2-photon process which is dependent on some process that's taking place in the electronic excited state. So we're a bit limited with our laser spectroscopy system in that we can't play around with these, we can't get any temporal information like some of these pump probe experiments I mentioned earlier. But what we do have is we have quite a nice wide wavelength range that we can study. So this is a contour plot which shows the mass spectrum on this axis the signal obviously on the vertical axis, and then the wavelength on this axis, starting with 220 nanometers and going to the origin of that bright pi star state. And what you can see is that when you're ionizing, what's interesting is that all of these ions start in the same place. So as soon as you access your electronic excited state, your bright singlet excited state, as long as you might need to absorb more photons, but you can, in principle, you can produce any of the fragment ions that are produced by electron impact ionization. The exception, well, there are two exceptions. One is our new peak at 84 atomic mass units, and then there's also a metastable channel, which I won't talk about here, but we've been looking at in some detail recently. So this has a distinctive energy threshold compared, whereas all the other fragment ions don't. And we can look at that in a bit more detail. This time I've plotted it on a photon energy scale. This is the dependence of the signal as a percentage of the total ion signal of our new fragment as a function of photon energy. And you see that we've got a rough threshold of about 5.3 EV. And we're lucky enough that another group has calculated electronic excited state crossings, so if you like, the intersections between different electronic excited states. And they've calculated how the molecule's geometry changes as it crosses between these electronic excited states, and also the energies at which these crossings take place. And you can see that these are for the crossing between our bright pi star state, the one that lasts for 50 femtoseconds or so, and our relatively long-lived singlet state that we're ionizing from. And you can see that you've got three varieties which all seem to show, some kind of bending of the molecule, but nothing that looks too damaging, nothing that looks too worrying from a radiobiological perspective. But then there's this exception where you actually see the molecule breaking, you're losing its aromatic structure. And this state, this excited state ring opening, they calculated the threshold for that at 5.25 EV, which seems to agree perfectly with the threshold that we see for this fragment ion. And then in addition, we can see that when we look at the geometry of that, we see a dangling CO that looks ripe for abstraction. And if you take CO, the mass of CO, 28 atomic mass units away from uracil, you end up with 84. And so this really looks like a signature of CO loss due to this excited state ring opening of uracil. So it looks like a new and quite interesting damage mechanism of this biological molecule. So the next question is, well, okay, how is this affected when we produce our hydrated clusters? And so here we've got a mass spectrum shown in red for isolated molecules, and in exactly the same conditions, but in the presence of water and with the formation of uracil water clusters here in blue. And in general, we see a relative enhancement of fragment ions that don't need a very high energy to initiate them due to clustering, and that's at the expense of some of the ions that need more energy. And that's understood, we understand that as being associated with energy loss from the molecule due to the evaporation of associated water molecules. However, our new peak at 84 is an exception to that. So what this is suggesting is that, well, it's certainly showing that in some way the water environment is stabilizing uracil with respect to this excited state ring opening, this excited state damage process, if you like. So it's offering some kind of radio protection. What exactly that process is, I'm afraid, we can only speculate. In some way, it's disrupting this crossing seam where that happens. But here we come to, a problem with our experiments, and a problem with lots of experiments in clusters, which is that you don't know for sure, in most cases, where your ion that you detect in your experiment actually came from. So it'd be very nice to run these experiments knowing that you've got uracil and one water molecule, and then you're already seeing this stabilization effect? Or do you need an entire closed shell of water molecules or something like that? But we don't have that information. There is a method that we're able to use which can give some extra information about where certain ions come from. And so this is a mass spectrum that you've got a mass spectrum along this axis, and then we've plotted it as a function of the reflect voltage, which is directly proportional to velocity on this axis. And you can see that essentially the further the peak goes, the higher the velocity of the ions. And this can contain an awful lot of information to help us unravel some specific fragmentation processes, and we're at a relatively early stage of analysing them. But what we can do is we can certainly tell the ions that were produced with no kinetic energy, with no velocity, with no transverse velocity. And in that case, we know that they didn't come from a cluster, because from a larger cluster. Because if you have a fragmentation of any kind, even a cluster fragmentation, you'll have some transverse kinetic energy of your fragment. And a nice example that we can get from this result, so this is looking at thymine clusters, and you can see that whereas protonated thymine does travel a certain distance, as you'd expect, that can only come from clusters, isolated thymine ions don't travel anywhere. So in our experiment, you can see that in our ionizing conditions, if you produce thymine, that only comes from isolated molecules in our beam, and you can't produce thymine plus from thymine clusters. So there's some information we can get about origins, but it's quite limited. And what we're trying to do now is get real control over our targets. And the tool we're trying to use for that is we're trying to exploit differences in dipole moment over mass ratios. And so this shows an example of if you wanted to study a natural target, study would be a Watson-Crick pair of guanine and cytosine in an experiment. But if you produce any normal cluster target, you're going to get all of these other species as well. You're going to get the two common isomers of gas phase cytosine, you're going to get guanine as well in there, you're going to get an alternative dimer complex, if you like, of guanine and cytosine as well, which isn't biologically relevant. And so what we're planning to do is, we've built an experiment, and we're working on optimizing it at the moment, to use the dipole moment over mass ratio as a tool to try to select specific clusters. And so this is a Stark selection type process. What we do is we set up a strong electric field. Our molecules travel in the plane, through this field, if you like. You'll get some alignment of the molecules, of the neutral molecules in the field due to their dipole moments. Well, dipole moments will tend to align in the strong field. And then we have a very strong field gradient, so that over the actual scale of the molecule, one side of the dipole finds itself in a slightly stronger electric field than the other. And so even though the total charge of the molecule is neutral, you do get a slight deflection. Oh my God, okay. I'm going to have to accelerate a lot. Yeah, okay. Yes, and so that's the method that we're trying to exploit. So again, we have a molecular beam. In this case, you need to really limit rotational excitation. That's a big challenge in these types of experiments, because that will blur out any kind of effect that I was talking about there. So you produce a very cold molecular beam, you pass it to your start deflector, then you have a physical skimmer that you can move across your beam to select different parts of your beam, and therefore select different clusters, different isomers within that beam, and then you cross it with a high-resolution electron beam and analyze anion production. And this has been, I won't talk you through this, but this has been, we're doing this project in collaboration with a group in Germany led by Jochen Köpper, and they've applied this technique successfully for laser spectroscopy experiments on indole water clusters. So indole, a molecule that looks a lot like the kind of DNA bases and molecules like this that we're interested in probing. So this brings me to one of the main motivations of our experiments looking at electron attachment to selected clusters is to draw comparisons with our collaborators at the Open University, Hermene Finkel, as I said, who's also in the RaBBiT program, so you'll have opportunities to work with her if you'd like to. And in their group, they've got they're experts in the so-called R-matrix method of carrying out electron scattering calculations, which works extremely well when you assume fixed nuclei positions, which means it's very well for electron scattering type calculations. However, it gets challenging when you have dissociative processes, when you have inelastic processes where you start to have the motion of nuclei in a molecule or cluster. And they are currently pioneering, in collaboration with Ilya Fabrikant in Nebraska, they're pioneering methods to look at inelastic processes in more detail and to calculate them more efficiently for relatively complex molecules and biological molecules, including and also clusters. And so we want to provide, if you're going to compare experimental results with calculations, you need to know that you're looking at exactly the same target. And so that's why we're really trying to, one of the reasons why we're trying to gain control over the target configurations experimentally. And their calculations have demonstrated, among other things, that the specific configuration of a cluster can have a very significant effect on electron attachment, as we expected earlier. For example, they've carried out calculations looking at CF3Cl in clusters with 3 water molecules, and they've tried putting those water molecules in different places. Obviously plausible places based on quantum chemical calculations. And they found that for, if you like, geometry A of the cluster compared to geometry B here, this is showing the absolute cross-section for the production of Cl minus from CF3Cl with 3 water molecules assembled like this around the molecule compared to 3 water molecules assembled around the other side of the molecule. And you see a huge enhancement of the cross-section for this dissociation due to the specific geometry of the cluster. So taking these kinds of effects into account is extremely important. And we want to provide reference data to actually be able to test these theoretical techniques. So, in summary, we've compared multiphoton ionization and electron impact and this has provided new insights into biomolecular reactivity in neutrally excited states, including the first experimental evidence for theoretically predicted ring opening in excited uracil. And experiments by us and calculations by Jimena have demonstrated significant clustering effects on molecular fragmentation processes. In our case, looking at dissociative ionization processes, in her case, looking at dissociative electron attachment processes. And clustering, so we've seen that clustering with water, for example, stabilizes uracil with respect to this excited state ring opening, and strong clustering configuration effects have been observed in the calculations for DEA to hydrated CF3Cl. And both groups are developing new methods, so we're developing new experiments to probe electron attachment to selected isotopes and clusters, and Jimena's group developing new methods to calculate inelastic electron-driven processes in clusters. And together, and independently, these can provide new insights into radiation-induced processes in biological molecules, biological material. And I've just put the websites for our 2 groups there, if you're interested in finding out more or potentially doing some PhD work with us. And lastly, I'd like to acknowledge my team, Marcin Damk, Mikhail Ryska, and Bartmelej Bark, and Rahul Pandey, who carried out the experiments. That's Mikhail Ryska, one of the PhD students in the group at the moment. My collaborators on the 2 main types of project that I'm working on, and also the funders for my group. And I'll leave that slide up. Okay, so thank you for your attention.
Any comments and questions, please?
Yeah, your last example with Cl- formation from this CF
3Cl, yeah.
Which showed even a higher cross-section than the clusters right?
Sorry? Well, the isolated molecule isn't shown in this plot.
Not shown.
So you've just got the comparison of two different geometries of the cluster with 3 water molecules.
We cannot compare in these calculations the cross-section of the isolated molecule.
I'm sure they did.
Because this is an example where even clustering could enhance
Absolutely.
the EA
Yeah.
due to light.
And that has certainly been, observed. Well, that's certainly a result from other calculations.
It's one of the
Yeah, absolutely, yeah.
Yeah, I missed something in the comparison of the multi-photon effects and the electron impact effects. In the case of the electron, it's clear that you have 200 eV, so a well-defined electron beam. But in the case of photons, the result of the dissociation used depends on the intensity of the laser.
It does.
Because the number of photons that you are producing.
You can test that though post. So what you can do, obviously, you can vary the laser fluence, but yeah, you can look at you vary the laser fluence, and you look at the signal as a function of laser fluence, and the power order of the dependence tells you how many photons have been absorbed.
So you are sure you're only using 2 photons?
For that, yes. To produce, for example, the fragment at 28, the CNH2, that is a 3-photon process. So we can test that.
The power, the intensity of the laser to be sure that you are only
Absolutely.
absorbing 2 photons.
Yeah, and for that you have to be very careful to watch out for saturation effects as well. So it's a delicate measurement that you have to carry out.
Do you compare also this multi-photon and the electron in this experiment when you measure the kinetic energy release?
No, because unfortunately, in the case of the electron impact ion, it only works because we can produce the ions with the laser at a very specific point. With the electron beam that we've got, it's quite diffuse, and we're producing electrons everywhere, so unfortunately we can't.
Okay, so, well, we have Sam there, and we are now